Well, to continue with our discussions, what we were discussing the development of an analytical model developed from basic physics in order to predict the flow patterns in a liquid flow systems under reduced dimensions from the principle of minimization of total system energy, where the system energy was postulated to comprise of kinetic energy, potential energy and surface energy of the two phases and between the liquid solid interfaces. Now, what we had assumed that this is particularly applicable for surface energy dominant phenomena. So, naturally kinetic energy induced instabilities like Kelvin-Helmholtz instability etc., they are not applicable in this particular case. And the other thing which we had assumed was quite common, which we usually assume, like fully developed steady state and smooth interface etc. And we had tried to do it for surface tension dominant situations. Therefore, we have confined our analysis for low to moderate velocities of the two liquids, and in this particular case the entire analysis was validated with the experiments performed in the multiphase flow laboratory with water and toluene as the test fluids. Now, since we were trying to confine our attention on low to moderate velocities, so naturally this particular analysis has been developed for the plug flow pattern, where we have assumed that we have neglected the nose region of the liquid plugs and we have assumed rectangular liquid plugs, in this particular case organic plugs, since water is the wetting phase. Organic plugs traversing through the continuous water medium, and there are water slugs in between the toluene slugs, and there is also water film encircling the toluene slugs. So, this is the idealized plug flow model that we have assumed, and the geometric parameters which we will be adopting for the analysis are also given here. We have taken up a unit cell, where each unit cell comprises of organic plug and one particular aqueous plug, such that the two combined together gives us the total length of a liquid slug, and the diameter of the plug has been taken as D plug and it is flowing in a conduit of diameter D. On the other hand, we find that for higher gas velocity, for the higher velocity of the other phase, the organic phase, we have annular flow pattern. So, we have assumed both situations. We have developed the model for a concentric core as well as for an eccentric core. In the eccentric core, we have assumed that a very small, very low thickness of liquid film is flowing on the top wall, such that they are almost touching, but yet there is going to be some particular interfacial shear between the organic and the water phase throughout. Now, these two configurations, why we have developed them? For very low dimensions, as we have seen, the flow is perfectly axisymmetric annular flow with the diameter of the core taken as D core, and as I have mentioned, for all cases the diameter of the pipe is D and the length of the pipe is L. Now, as we keep on increasing the dimension of the conduit, we find that there is a tendency of eccentricity, or the core appears to be eccentrically placed. So, we have developed models for, or rather energy equations for both of them, such that we can see that under what condition the eccentric annular flow becomes more stable than the concentric annular flow, or in other words, eccentric annular has got lower energy content as compared to the annular flow pattern. But in both the cases, we have assumed smooth interfaces between the two liquids. Now, as we know that as we increase the liquid the conduit diameter more, then there is a tendency of stratification. What happens under that condition? The organic phase, it starts touching the upper wall, and then we find that the entire conduit is divided into two areas, where the upper portion occupied by the lighter phase, which in liquid cases is usually the organic phase, and the lower portion it is occupied by the aqueous phase, where this particular aqueous phase or rather for our case it is usually the aqueous phase which occupies here. Now, since we are working with your small diameter systems, so therefore, we have assumed that the interface separating the stratified flow, it will be a curved rather than a plane interface, and we assume that this particular curve it is a circular one, and the analysis for developing the equations for stratified flow have been taken from the analysis of Browner et al., and that can be found out from the reference of the paper which I have already referred. So, in this particular case we find that the height of the center of gravity is h2 and the height of the center of gravity of the the height of the center of gravity of the water portion is h1 and that for the toluene portion is h2, and we find that the entire geometry it is represented or it can be represented by two particular angles phi 0 and phi star. So, therefore, as I was telling the don't find the pen anyhow, for an annular flow there are two things that we have assumed, but both these assumptions they are extremely valid as we have observed from our experiments. The number one is negligible energy dissipation due to wall friction, which is valid definitely for low viscous liquids. Again, I would like to mention that this analysis is applicable for low viscous liquid flows, and the other thing is no amount of wall liquid is entrained in a core, which is also a very reasonable assumption as far as your small diameter conduits are concerned. Accordingly, the expressions for the change in potential energy with respect to the reference substance, which is water flowing at the mixture velocity, has been developed. Now, this analysis it can very well be done by considering the geometry. I am not going into the details of this analysis. Similarly, we have performed the analysis for eccentric core annular flow. As is evident that the kinetic energy and the surface energy terms they are going to remain unchanged for eccentric core. The only thing which changes is going to be the potential energy term. Why? Because the center of gravity appears to shift in this particular case. So, accordingly, the potential energy term it should be actually delta Pa, there is a typo here. So, this particular term this has only been developed, and the surface energy terms from the kinetic energy terms from the concentric core has been adopted. The three have been added up to give us the total energy term in this particular case. Similarly, for the stratified flow case also, as you can see, we have developed the potential energy, kinetic energy and the surface energy terms in this particular case. We find that the surface energies they are governed by the two angles as I have mentioned phi 0 and phi star, and they define alpha and the other geometric parameters. Well, we have also done it for slug flow as I have mentioned axisymmetric cylindrical plugs. Now, in this particular case we find that there is one more unknown, which is the length of the plug. This is the only parameter which has been taken from a correlation which has been developed from experimental data, and we have used not only our experimental data, but also data from literature to develop this particular correlation, which gives us the plug length with respect to the diameter of the conduit in terms of the velocities of the two fluids as well as the diameter of the conduit, where the diameter is in millimeters. Now, what we have done? We have non-dimensionalized the total energy and we have expressed it in terms of non-dimensional groups. If we now observe the non-dimensional groups, what do we find? We find that the same dimensionless numbers are appearing in the total energy expressions of annular, eccentric annular, stratified and the plug flow pattern. What are the groups that are appearing? At first appearance you see it is the Froude number and the Weber number of the mixture. Apart from this, the other important groups unnaturally inlet volumetric fraction of the two phases, in situ fraction of the two phases. That is it, I do not find anything else. Only in the stratified flow expression we have the bond number of phase 1 and phase 2, which is quite expected. So, therefore, what we find that the same dimensionless numbers are appearing in all of them. What we do? We first plot, rather we first develop these particular expressions, then for a given alpha, for given flow conditions in a particular pipe diameter for two particular fluid pairs, so that we know all the physical properties of the fluid. We know the for any particular alpha, we can compute the total energies for different distributions. The flow chart is as shown. You can follow the flow chart and use it for predicting the stable flow pattern in this particular case. And after developing the flow chart, what we do? We have plotted the total energy term as a function of alpha. And here what do we find? Very interestingly, you will find that for higher alpha values, we find that water wetting annular flow is applicable. Since in this particular case, we have just plotted from 0.78 to 0.98, we find that the water wetting annular flow is the has the minimum amount of energy, and interestingly we find that the difference between stratified and water wetting annular flow, it decreases as we shift to lower alphas. We have not plotted beyond it, I will be showing it in another particular slide. And I would also like to mention that we have developed this, rather I have discussed this model assuming the tube to be hydrophilic. In other words, we have, since we are going to validate it for toluene water flow in a glass capillary. So, therefore, it is a hydrophilic tube, and you can very well see for this particular situation, we have got the water wetting annular flow as the most stable, and you can very well see that the toluene wetting annular flow is much unstable. We will see a reverse case later on in one of the slides, where we will be working with a hydrophobic tube. So, therefore, once the model was developed, the algorithm was developed, we could use the model, and then after that we wanted to extract some more extra information from this. So, for that what we did, we tried to plot the influence of diameter and the water fraction, because we found out from this particular expressions, if you observe, we found out that diameter is the diameter is the most important parameter for defining the total energies. So, that explains why when previous researchers had used hydraulic diameter to classify the channels, more or less accurate results were obtained. So, after developing the energy equations, now let me tell you certain things. What were the postulations that we use to decide the stable flow pattern? Firstly, the energy expressions were derived. The pattern which had the lowest energy, for example, in this particular case it was the water wetting annular flow pattern, was considered as the stable flow pattern, provided it had energy substantially less than the other flow patterns. If the energy difference between two patterns was less than 7.5%, we assumed that either of the flow patterns can exist. So, naturally it must be a transition. The other thing which we had considered was, for the plug flow pattern, it is quite evident that the plugs cannot become indefinitely long and they cannot occupy the entire channel. So, therefore, there must be some particular limiting length for the plug flow pattern to exist. Based on our experiments and data from literature, we have postulated that L plug by D, it should not exceed 10 to 20. Okay. So, therefore, this was the only thing which we have assumed. I have also referred to this also. So, therefore, the length of the plug should not exceed 20 times the diameter. So, based on these three postulations, firstly the minimum energy, Secondly, the energy difference between the most stable pattern and the next higher stable pattern should not be, rather should be greater than 7.5%, otherwise it lies in a transition, and if it is plug flow, then a check on the plug length. Based on this, we had developed the stable flow pattern, or rather we had developed a flow pattern map, which is there in the paper. I have not shown it here because I wanted to show some other interesting aspects which have come out from the model. So, therefore, do we see? We find out that for low diameters definitely and low the low 1 minus beta, plug flow pattern is more stable. It is quite obvious. We find that when the water fraction is higher and at the same time the diameter is lower, then under that case we get the plug flow pattern. Okay. And as we decrease the water fraction, we gradually shift to the annular flow pattern. And again we have plug flow pattern here, we had plug flow pattern here, and from the plug flow pattern we find that as we decrease the water fraction we get annular flow, as we increase the diameter we get annular flow. So, therefore, there is a coupled effect of decreasing beta and increasing diameter to attain the annular flow pattern. Now, if we keep on increasing diameter, keeping the water fraction same, we find that gradually the concentric core it becomes eccentric, and then again if we increase the diameter further it becomes stratified, and as we increase the diameter the interface it shifts from a curved interface to a flat interface. So, therefore, this particular graph gives you an idea of the influence of diameter and the volume fraction of the two phases in a pictorial fashion, just to understand how diameter and beta they complement each other in deciding the flow pattern. We have also noted down the surface energy, potential energy, kinetic energy, and also the total energy of the four situations which have been depicted here, just to highlight the dominance of surface energy in deciding the plug flow pattern, and how the even if the surface energy is not so very high for larger pipe dimensions. Well, after this the diameter effect, since the diameter is so very important, we found, so that for the diameter effect has further been plotted or rather the total energy change of the two phase system has been plotted as a function of diameter for two different inlet Tollin fractions, one is 0.5, the other is 0.9. If you observe the curves minutely, what do you observe? We find that for beta equals to 0.5, it is very evident that for low diameter situations, what is stable? Plug flow pattern is stable. Then for a very low diameter range, we find that the annular flow it appears to be stable. Sorry, not annular, very sorry, it is the stratified flow. Beyond a particular diameter, we find that it is a stratified flow which is stable, and I think here the annular flow is stable. For some particular small diameter range, the annular flow is stable, and beyond that we find that the stratified flow is stable, but in this particular case initially we find that the stratified flow has comparable total energy with the eccentric core annular flow. This is what is expected. So, therefore, we find that for low to moderate water fractions and for small diameters we get only plug flow pattern, and beyond a particular critical diameter, which in our particular case of water Tollin flow we find is about 1.5 centimeters, we find that stratification exists for both beta equals to 0.5 as well as for beta equals to 0.9. So, therefore, what do we find? We find that when we are operating at moderate water fractions, initially the plug flow pattern is stable, then gradually annular and stratified they compete with each other, and finally the stratified flow pattern becomes more stable. Just keeping everything constant, the mixture velocity etc., we just shift from, rather we go to a higher toluene fraction. Very interestingly, what do we find in this particular case? In this particular case, we find that for low diameters, in this case plug is not stable, but the annular flow pattern is stable. Annular flow pattern continues to be stable till the critical diameter, which is around 1.75 centimeters in this case. After that, it is the stratified flow which becomes stable. So, therefore, from here what do we understand? It is very evident that the stratified flow exists for some particular critical diameter. For this particular case of water toluene flow, we have observed the critical diameter to be 15 centimeters. Quite evidently, the diameter will be a function of phase physical properties. It is a weak function of the inlet volumetric fraction. And below critical diameter, we find that the plug and annular, they compete to be the energetically more privileged flow pattern. For a low to moderate water fractions, the plug flow pattern is more stable, and for higher water fractions, the annular flow pattern is much more stable. And the other interesting thing which we have observed, we have done it for 3 betas, and we have also in this case we have plotted it for a hydrophilic tube, or rather we have considered glass where the contact angle is 30 degrees, and we have also done it for a hydrophobic tube where the glass was coated with silane and the contact angle with water was observed to be 120 degrees. In this particular case, we find that when it became hydrophobic, the tendency of forming a stable water film decreased, and therefore, in this particular case, if you observe properly, we find that the annular flow with toluene wetting, that is the most stable as compared to annular flow with water wetting case. And interestingly, we find that in this particular case, since water has a very less tendency to wet the pipe wall, the stratified, the onset of stratification is shifted to a much higher diameter. So, therefore, these are these were the interesting things that we could observe from this particular diameter, rather from this particular analysis. Well, another important thing is from here, so what are the things that we could get? We could predict the stable flow pattern, that was first. Next, we could use the analysis to predict the stable flow pattern both for hydrophobic as well as for hydrophilic cases. We could also predict the zone of transition, and very interestingly, from this particular case, we could also predict the domain of microchannel and the domain of macro system. For example, for our case, we find that for hydrophilic case, we found that the stratified, the onset of stratification started beyond 15 centimeters. Sorry, yeah, it was started beyond, I think 15 centimeters, isn't it? No, it started beyond, yeah, 1.5 centimeters, sorry. So, therefore, in this particular case, what we postulated was that definitely the transition from micro to mini should occur when the distribution shifts from symmetric to asymmetric distribution. So, therefore, we assumed that for microsystem, concentric core annular should have the minimum energy. As the energy of concentric and eccentric core started becoming comparable, or the difference was less than 10% and above, when the eccentric core became more stable as compared to concentric, we assumed that it is the onset of mini channels. So, therefore, the transition from micro to mini was postulated as occurring when eccentric core became more stable as compared to concentric core, and the transition from mini to large or conventional channels was postulated when stratification came into picture. So, therefore, based on this, we found out the critical diameters, and since it is a common convention, as we had seen in the last to last lecture, that usually the domains are expressed in terms of bond number, So, accordingly we also expressed it in terms of bond number, and we found out that the onset of asymmetry which is marked by comparable energies, comparable total energies of eccentric annular and concentric annular flows. This occurs for a bond number close to 0.1. And the onset of stratification that occurs for a bond number close to 10. So, accordingly what we postulated was that the range or the domain of millichannels that occurs between, rather that can occur, where I would like to mention that this is the, I should write this is the bond number of the two phase mixture. So, therefore, we find that the range of mini channels is 0.1 So, this is the range of mini channels that we obtain in terms of the two phase bond number, and it will be interesting to note that if you compare this particular value with the table that I had shown yesterday, you will find that all the transition values which were given by the past researchers, they lie within this particular domain. So, therefore, this model could predict a large number of things, and I think we have not tried it, but this should be quite applicable for your gas liquid systems, slightly inclined flow patterns, and also it should be it can be used for other flow patterns as well. Now, before I end this particular session, I would also like to mention just a basic difference between two phase flow and single phase flow. In two phase flow, we found that it was that the physics of flow was very different in mini or micro channels as compared to your macro systems or conventional systems. Therefore, it was essential to define the range or the domain of micro systems and mini systems. In single phase flow, if we find that suppose it is just water flowing through a micro system, usually it is noted that the equations for laminar and turbulent are applicable for that case as well, and the critical Reynolds number is also close to 2100 2000 in this particular case. So, therefore, the equations which have been developed for conventional systems can be applied for your micro systems as well. On the contrary, for single phase gas flow, we find that when we go for micro systems, we find that the no slip condition is no longer applicable, and there is a slip, along with that there is a temperature jump also, and therefore, the range of microchannel needs to be defined for only gas flow, and this particular range it is defined in terms of Knudsen number, which is defined as Kn, and it is equal to lambda by L, where lambda is the mean free path and L is the characteristic length of the conduit. So, we find that when this Knudsen, based on this value of Knudsen number, the micro effects in gas flows appear, and as a result the normal equations for macro systems cannot be used. For example, we find that for Knudsen number greater than for Knudsen number less than 10 to the power minus 3, we find that the continuum flow is applicable. So, it can be modeled by Navier-Stokes equation, and no slip condition is also applicable. But as we go for higher and higher Knudsen number, we find that the no slip condition is no longer applicable, and there is a velocity slip between the wall as well as the gas, and the Navier-Stokes equation, although it is applicable, but we have to incorporate velocity slip and temperature jump there. Then again, if we go for a still higher Knudsen number, we find that then Navier-Stokes equation is no longer applicable, because under that condition wall fluid particle interaction becomes much more important as compared to intermolecular collisions, and then for still higher Reynolds number we find that it becomes a free molecular flow and the single phase equations are no longer applicable. So, therefore, this was just to give you an idea about how two phase flow is much more different than single phase flows, and we should keep it in mind while modeling or dealing with any particular situation of two phase flow. Thank you very much.